Good afternoon. I hope all is well. My name is Michael Core. I am a PhD student in Earth, Ocean, and Atmospheric Science at Florida State University under Dr. Ming Yi. I've been working with my associate, Wei Mao, on studying septic tanks and septic tank setbacks here in Florida. This demonstration is to give more information on running and calibrating the ArcNLET-Py toolset that's available in ArcGIS Pro. We will look at the study area of Turkey Creek, and we'll walk through each module of the ArcNLET-Py and go over some advanced topics, including data preparation, running the modules, and examining your results. Firstly, ArcNLET-Py is the ArcGIS-based nutrient load estimation toolbox from Python. If you have not done so already, I would suggest that you go to our GitHub repo and check out github.com/arcinlet-py/arcinlet-py. Here's our GitHub repo. It has a great README to get you going. And down here at the bottom is our user manual. If you have not read through the user manual, I would highly recommend you working through the Lakeshore example, which is intended for beginners, which needs no model calibration. Once you are finished with this example, then you can come back to this Gross, Close, and Jones example and experience the entire model, including calibration. Keep in mind that modeling is a cyclical endeavor. It involves obtaining data either through collecting it in the field or from literature, understanding model domains, processes, and parameters, running the model with a beginning set of parameters, and getting the outputs, comparing the outputs with your data from the real world, then adjusting the model based on common practices such as root mean square error or a one-to-one slope line, and then running the model again. Running the model could take many iterations to get satisfactory results. It never happens in one instance. Our study area today is near Melbourne, Florida. It's in the Turkey Creek Sub-Basin. It's a part of a neighborhood subdivision with residential housing that represents an urban area. This is a great example to help show the impacts of OSTDS on the surrounding surface water bodies. To begin with, we must prepare some input data. The necessary requirements are that you need an ample study area that is of great enough size. You also have to get OSTDS or septic tank data. This is generally done in the form of parcel data that's available from the Florida Department of Health, Florida Wastewater Management Inventory Project. Here, parcel information is available. If you click from FTP, you will get a list of all of the needed counties here in Florida. You can click on the county of your desire, and then here you will find the zip file. Inside of the zip file is a shapefile. The shapefile contains all the parcels for the county with a designation of wastewater type. Here we can see an example of what the downloaded data would look like. In here we have many wastewater types, what known, likely, or somewhat likely for the septic tank type. So pretty much anything in our list here that says septic, we want to filter for that. Once we filter, we need a point location to run ArcNLET. We can see here's an example of some of the septic tank locations that have been turned into point with known septic tank types. You can see the red dots representing the parcel centroid on the map. This is the quickest way to get a roundabout parcel location and a roundabout OSTDS location. For some areas, specifically in the grow close sites, we know the coordinates of the gray water tanks and the black water tanks that can be seen in this figure. These were gotten from the Ayers and Associates report from 1993. The OSTDS locations are the first important piece of data that you'll need. The next consideration, our study area needs to be large enough to include the two properties that we're interested in, which are the Jones and the Grosclose, as well as surrounding hydrologic features with a constant hydraulic head, which can be seen along the north of the study area where there's a drainage canal, along the west of the study area where there's a drainage canal, along the east of the study area where there's a drainage canal, and along the south of the study area is a man-made feature, such as a major road data source that we have to work on are the water bodies. Many times when we download water body features, they come in a combination of polygons and flow lines. Unfortunately, flow lines have no widths and therefore are not compatible with ArcNLET-Py. ArcNLET-Py needs the water bodies to have a width to be able to truncate the flow paths of the nutrients into the water body. We must use outside data sources such as Google Earth, Google Maps, or the Properties Appraiser EagleView to find these water bodies and estimate a width. Here in the screenshots, we can see the water bodies along the course. We can go to Google Earth and we can view the canals that run along the north of the study area. Likewise, we can see the canal that runs along the west of the study area. Once we have an idea of the width of the canal, we can come back into the GIS and we can modify our water body features. So to begin with, we have our NHD flow lines. These are inadequate because they do not have a width. Here are our NHD water bodies. Once we estimate a width for our flow lines, we want to merge the flow line polygons with the NHD water bodies to create our data set of water bodies inside of our study area. The next piece of information that's crucial for ArcNLET-Py to work are digital elevation models. Digital elevation models can be gotten from the same data source as our hydro flow lines and our water body features. We would want to come to the USGS, the National Map Downloader Volume version 2, select the data sets that we need, which in this case is the 3DEP elevation product, and then we would do a search. Afterwards, we would download our data. Here we can see an example of digital elevation model data. Another note about choosing your digital elevation model: after many, many trials, the 3x3 model, the 3 meter by 3 meter digital elevation model seems to be well suited for ArcNLET. The 10 meter by 10 meter digital elevation models are too coarse and sometimes can cause errors where water bodies are skipped over, as well as the 1 meter by 1 meter models are very complex and they have a lot of variation in the data sets, which are not necessary for estimating the smoothness of the groundwater surface. We have a study area, a digital elevation model, water bodies that have been estimated, and OSTDS parcel centroids that are known, likely to be known, or somewhat likely to be known to have septic tanks. We can move on to using ArcNLET-Py. The first step is to run the pre-processing module. The pre-processing module aids in getting soil information from the Surgo database. The soil information that we're concerned are hydraulic conductivity, porosity, soil type. For this demonstration, our soil depths are between 79 centimeters and 201 centimeters. In general, for extracting hydraulic conductivity information, we always want to use the harmonic mean for hydraulic conductivity as to not skew our results. Another important consideration is that we want our results to match the cell size of our digital elevation model. In this case, it will be 3 meters. access the pre-processing module in ArcGIS Pro. We want to come and find our toolbox wherever we have extracted it. Now we'll use our study area that we created with regards to hydraulic boundaries and man-made boundaries. Then we always projections are in meters. We find that the UTM works very well with ArcNLET-Py. We want to change our soil depth. Now this is crucial to running the model. We need to set output locations. These cannot be file geo databases. If the default output location tries to be a file geo database, please change this to a folder. ArcNLET-Py only works with folders, shapefiles, and rasters. Now we're going to save our porosity raster in the same directory. Likewise for our soil type. And just in case, we'll save this one also. Once we have everything in place, we click Run. Once the pre-processing module is run, we should see our outputs, hydraulic conductivity, porosity, soil type, and the spatial outputs of the study area. Iterative process, and each module builds upon the last, meaning that outputs from the previous module are used as inputs in the subsequent module. We can move on to the groundwater flow module now. Here you'll see the digital elevation model that we downloaded from the USGS, the National Map Downloader, as well as the water body features that we had to add widths to. Sometimes water body features are missing altogether from the NHD. If you notice that you are missing ditches and canals and other water body features, you will want to add them before running the groundwater flow module. The groundwater flow module uses the water body elevations from these shape files to help better estimate the shape of the groundwater. To run the groundwater flow module, first we will define the digital elevation model, then we will define the water bodies. As noted before, we'll need the data outputs from the pre-processing module. So we'll come over here and grab those. Here we'll add in all the information. And as we did before, we need to ensure that we're saving everything into the file system. First, we're going to extract the velocity magnitude. Then we'll extract our velocity direction. We can save the smoothed DEM for running VZMod or checking the results of the ground flow module against field estimation. And then we can also save the hydraulic gradient. The parameters here are very important. Adjusting these smoothing factors and the smoothing cells can take many, many iterations. Here, we'll go ahead and enter some information that we've already deduced works well with our models. So beginning, we want to do a smoothing factor of 10 and a smoothing window or smoothing cell size of 31. We want to merge the water bodies. This means that we're going to, after each smoothing iteration, we're going to bring our water body elevation back in and reset it. That way we don't lose our water bodies after the smoothing. Now we're going to smooth for several more iterations in a decreasing manner. We always want to do in a decreasing manner because we're helping to encourage a gradient near the water bodies. We don't want to over smooth because we're going to simplify our landscape, and we don't want to under smooth because our landscape will be too complex and our water bodies will not flow reasonably into the surface water bodies. It is very important to have a gradient in the smoothing cell size because this helps avoid trapped particles at the edges of water bodies where there could theoretically be gaps between the soil surgo data and the water body data sets. Once we have the groundwater flow set up in a similar manner with a gradation of smoothing factors and smoothing cell sizes, we want to run the operation. There's a couple of ways to check the results of the groundwater flow module. One is to use the output smooth DEM and known locations of groundwater and extract the locations. For example, we know that we have well locations with information as shown in this table. Each one of these well locations has a total depth and a groundwater elevation and a top of casing depth. We can use this information to help estimate where the groundwater will be. With these types of values, we can extract our values from the smooth DEM and create a one-to-one line to estimate how well our smooth DEM is representing reality. Okay, to check if the groundwater flow module has run correctly is to run the particle path module and observe the particle paths. If you see particle paths with very strange squiggly lines or that appear that have become trapped or do not flow reasonably, as you see in the top figure with the red thumbs down, this means that the groundwater flow module needs to be revisited. If you see reasonable flow lines that are smooth, that seem to reasonably flow into surface water bodies along the elevation and hydraulic gradient of the landscape, then you are probably on the right path with the groundwater flow module. A consideration is that the original digital elevation model will have a lot of variation. Once it is smooth, it could have much less variation. And many times, the variation of the water bodies can be taken out of the digital elevation model. This is why it's so important to merge the water bodies back in after each smoothing iteration. These figures demonstrate the difference between the original digital elevation model and the digital elevation model that's been smoothed many times with the water bodies added back in. We can see how we compare the monitoring well with hydraulic head data reported in Ayers Associates 1993 with the simulated values to get our y-intercept and a slope. Satisfied with the groundwater flow module, we can run the particle tracking module. Here are the results from the groundwater flow module in ArcGIS Pro. As stated before, we can see the smooth DEM, we can see our direction raster, which are angular directions between 0 and 360 degrees, and then we can see our magnitude raster. We can also see the locations where we've extracted values from our smooth DEM, which you can see here. Here's the raster values of the DEM. Here's the feet measurements from the groundwater table converted to meters. Now we can compare the two to make the one-to-one line that we saw earlier. The particle tracking module depends on the groundwater flow module being run successfully. Particle paths will not be accurate without a successful run from the groundwater flow module. Here we can see particle paths in light coral that have been run correctly. They travel from the OSTDS location seen as black dots to the surface water bodies seen as yellow. Now we'll run the particle tracking module in ArcGIS Pro. First, we'll go to Catalog, open the particle tracking module. For this module, we will tracking module include the last piece of input data that we had to create, which are the OSTDS or septic tank locations. These should come from literature, field surveys, or from the Florida Department of Health database. The other input data sources that we need are the water bodies that came from the NHD that we had to also correct, our magnitude and our direction, which are outputs from the groundwater flow module, and then our porosity, which was gotten from Surgo by the pre-processing module. We'll move all of these data sources into the particle tracking. It'll make it easier to select them from the drop-down menu. To keep track of the smoothing factors that you used in the groundwater flow module. Here you can see that I've named my particle paths 10, 10, 10, 5, 2, which are representative of the smoothing factors that I used in the groundwater flow module. This helps keep track of things when you have to run many iterations to get the correct results. As far as the parameters go, they should be automatically updated with your data set, but we will want to truncate the flow lines at the water bodies. This is for visual purposes and doesn't actually change the load estimation results. You can see the outputs of the particle paths as they travel from the OSTDS to the surface water bodies. The particle paths seem reasonable. VZ-mod is to simulate interactions in the vadose zone as a one-dimensional vertical attenuation factor. We can simulate ammonium, nitrate, and phosphate. The most important parameters for adjusting in the VZ-mod are your nitrification rate, denitrification rate, phosphate precipitation rate, and your absorption coefficient. The goal is to have your VZ-mod output match the concentrations at the groundwater table. It is helpful if you have information as far as the source concentrations found in the septic tanks. For our situation, we have this information from Ayers and Associates. For instance, well G5 was determined to be in the middle of the septic tanks. And we can look here and help use these numbers to calibrate our model. This can be seen here from the field surveys from the report, where we have G5 right here between the septic tanks, which helps us to estimate the source plane concentration. We have the same thing with J11 and J9 here at the Jones house. We have a couple of options to choose based on our modeling preferences. You can see the information here that's also from Ayers and Associates. They specifically measured the gray water and the black water for the grow close residents. Here we can see how the different parameters in VZ-mod are adjusted. VZ-mod can take individual soil types, or it can use the soil type raster that we generated through the Surgo DB database with the pre-processing module. The hydraulic parameters can be adjusted based off of report data. In this situation, we have a wastewater loading and an average water usage that was found in the Grow Close and Jones reports that can be seen here. We were able to use this information to help estimate the hydraulic loading rate in VZ-mod. After VZ-mod was run for gross close, we could compare the estimations for the black water and the gray water to well G5. And we get an estimate at the source plane and at the groundwater table. Likewise, we can run the Jones site in the same manner, and we can use the information from the report to help estimate our starting points. Likewise, we have wells to compare the information to see if our model is on the right track. Once we have estimated the Jones site and gross close site individually, we can estimate both of them together. To the VZ mod in ArcGIS Pro. The VZ mod is useful for estimating the nutrient movement from the OSTDS through the saturated zone to the surface of the groundwater table vertically. This is a vertical one-dimensional flow. As before, we need the outputs of some of the other modules to estimate this. For starters, we'll need our OSTDS point locations that were used in the particle tracking. Here, we'll change our parameters for nitrogen and phosphorus. We want to look at multiple OSTDSs. In our situation, they're the Growth Close and Jones sites. They do share a similar loamy sand. And now we'll use our calibrated information that was deemed good enough from running each site individually. Mind you, these figures originally came from our report. We will get a results text file that's useful for making plots of the vertical profile of nitrogen, phosphate, and ammonia. We're going to change the hydraulic loading rate, our nitrification, our denitrification. We're going to change this to the Langmuir. And once we have everything in, we will want to run this. As stated before, modeling can be a cyclical process. You may not get everything completely right the first time. One of our outputs we'll see here. Here you can see the vertical profile of our concentrations for NH4, NO3, and PO4. These are very useful. You can plot each concentration against the depth in Excel and get a vertical profile to get a visual representation. These source plane concentrations then can be used in the transport module. Our outputs from the VZ mod will be used as inputs in the transport module, along with a few other things. The transport module is very important because it calculates the two-dimensional attenuation horizontally along the surface of the groundwater to the surface water bodies. Our important calibration aspects are the Delmonico boundary, the source place dimension, the longitudinal dispersivity for nitrate, and the horizontal dispersivity for nitrate, ammonia, and phosphate. It is important to know that you may have to run the model several times with different horizontal and longitudinal dispersivities. It could be helpful to create a matrix as you see here and keep track of each set. For this situation, this is the NO3 root mean square error for grow close. So I have pairs of each, and then we run the simulation multiple times. Next, we take the root mean square error by comparing the known measurements from our study, as we can see here, for each well location. And that's a reminder that we saw here for each well location. And then we can compare them to our simulated results. We can make a visual cue to help us understand how we travel towards or away from a better root mean square error with each pair of longitudinal and horizontal dispersivities. Likewise, we can do this for the combined data set. Furthermore, if anything else is giving you trouble in ArcNLET, such as the VZ mod, it is highly recommended to set up a matrix for K nitrification and denitrification in a very similar manner. This way you can run through each pair in an organized manner, documenting your results for posterity reasons. Here we can see the transport module in ArcGIS Pro. We want to look at nitrogen and phosphorus, and we want to consider NH4. Our input water bodies are going to be the same that we used in the VZ mod. Our input OSTDS locations will be the same that we used in the VZ mod. The water bodies and the particle paths will be the same that we used in the particle tracking module. Raster plume outputs for NO3, NH4, and PO4. This is very similar to the VZ mod. An important consideration is the source plane dimension. This is the theoretical size of the OSTDS. Other considerations, as we stated in the slides with the root mean square error matrix, are the longitudinal and horizontal dispersivities. Once we have all our parameters in place, we'll run the module. Once the transport module is finished, you will notice the messages in the geoprocessing history pane. Please note that the tool is having trouble. Your file paths could be an issue. It may be recommended to use a file path on your local C drive, similar to these right here. ArcGIS Pro does not like file path strings to have more than 128 characters when working with rasters. Also, sometimes OneDrive can have issues with schema locking and not being able to release the locks fast enough for ArcGIS Pro's liking. If you continue to have problems with the transport module, please try a local folder with a file path name that is not too long, as well as raster names that are less than 11 characters. Once the tool is complete, we'll have a couple outputs. One, we'll have plume shapefile information for each analyte that we chose. And we can see the concentrations here that have to do with all of the calculations made in ArcNLET. You can see water body IDs and everything else where the plumes make it to. We can see our dispersivities, we can see our source values, all that good information that we put into the different modules. One of the most important outputs of the transport module are our raster plumes. So as you'll see here, we'll have raster plumes for each analyte that we measured, PO4, NH4, and NO3. Just so you can see here, we can style these so that they're a little bit more appealing. Turn off the RA, and now we can see the NO3 plumes for each location. And you can do the same for NH4 or PO4. Once you're satisfied with the results of the transport module, you can move on to the load estimation module. Just be mindful, you want to check root mean square error as we talked about before by taking the values from the raster surface at the locations of the monitoring well and then comparing those with the values taken from your report as we have here in Ayers and Associates. So we would want to check these locations and we would want to compare them against our estimated values. Now that we're satisfied with the transport module and it has a satisfactory root mean square error, we can move on to the load estimation module. You may want to plot out your root mean square errors for all of your longitudinal and horizontal dispersivities. That way you can ensure that you have a good low root mean square error and you can prove that you've made it all the way through the modeling simulation process by trying many different simulations to get accurate real-world adjacent results. Now that we're done with the transport module, it's time to move on to the load estimation. In the load estimation, all of our inputs come from the outputs of the subsequent model. So for this one, we want our plume info shapefiles from the transport module. This is the information that the load estimation module is going to use to help estimate the loads for these. Here we go. Now we'll set up the module. And it'll automatically try to put the output CSV files where the input plumes existed. Another thing that we can put in is a risk factor. So if we have an engineer style risk estimate, this can multiply by our results. The load estimation tool runs very quickly. And we can see the outputs here, as well as in the CSV files. No output information for PO4. We can come back over here to the transport module and look at the plume, and we can see that these PO4 plumes did not actually intersect with the water body. That's why there's not a load estimation in there. And here's our CSV files for the results. We can open each individually. And what you'll notice is that we have a water body identification number from the geographic information feature ID. We have a mass output load times the risk factor, in this case was 1, a mass input load, which is the amount coming from the source plane, and then the mass removal, how much was removed along its trip through the vadose zone into the groundwater through nitrification and denitrification processes. Here's NO3. You can see the same style of information. And PO4. And as stated before, the PO4 does not reach the water body, so we don't really get any information in there. Review. Remember that the pre-processing module needs an accurate study area, projection coordinate systems in UTM meters, and accurate soil depths. The groundwater flow module needs adjusted smoothing factors, adjusted smoothing cell size, and emerging water bodies. The particle tracking module you must verify that the flow paths make sense and flow naturally into surface water bodies. If they have zigzagged or jagged lines, or particles are trapped in ditches or canals or in front of water bodies, then you must revisit the groundwater flow module. For the VZ mod, you will calibrate using field measurements, adjust nitrification, denitrification, and phosphorus. Then for the transport module, you'll want to adjust dispersivities and calibrate with monitoring well data. Finally, for the load estimation module, you will use the calibrated results from the transport module to produce accurate load estimations. If you're working with extremely large study areas greater than 1,000 OSCDS, you must manage your workstation accordingly. You may want to divide the domain into smaller sections or adjust the maximum plumes of continuous calculations in the transport module, which adjusts how many plumes are saved in your temporary memory per calculation cycle. Finally, here's some resources that you may need. Of course, our GitHub. Then there's more training videos available on YouTube. Documentation is available at FSU. You can get your digital elevation models and your water body data sets from USGS, the National Map download. And then for the OSCDS, if you don't have locations from a field study or literature, parcels are available from the Florida Department of Health Florida Water Management Inventory Project. Lastly, there's a list of plume studies that are available from the Florida Department of Environmental Protection at the link below. These have been vetted by Dr. Gao. Thank you so much. Have a great day.